Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss particle in a one-dimensional box or infinite deep potential well. Let's begin. The particle is trapped in a potential well and is also called the particle in a box. Such a potential box can be described by the zero potential region from minus A to plus A along x direction or along x axis as we consider the one dimensional box, and an infinite potential somewhere else, that is the potential function, the value of potential is 0 in what region? In the region that is from minus A to plus A. In that region the potential function will be 0 and the potential will be infinity at what region? That is x magnitude is greater than A, means outside of that of box. Let us consider that potential box. Here we choose potential box like this. This one with the origin at O, minus A to plus A, this is x axis, and here the potential is infinity, here infinity, and other point also infinity, and here the potential exists, that is Vx, of x. This is the potential. Inside that of region minus A to plus A, the value of potential will be 0, and outside that of region the potential will be infinity. Since the motion of the particle is restricted only along the x axis, that means from x is equal to minus A to x is equal to plus A, then the time independent Schrodinger equation for that of particle independent Schrodinger equation for the particle is psi double dash x. Double dash means that is just second order differentiation, plus 2m divided by h cross square e minus v of psi of x is equal to 0. That is equation number 1. This is the time independent Schrodinger equation, as that particle is restricted along that of x direction from minus A to plus A. Now, what should be the wave function of that particle outside of the box? First we calculate wave function of the particle outside the box. Magnitude of x greater than a. Let we denote the wave function of the particle which is outside the box be psi naught x, denoting wave function of the particle outside of the box by psi 0x, psi outside, psi o of x. Hence the equation changes to, hence equation 1 becomes psi o double dash of x minus 2m by h cross square v minus e psi naught of x is equal to 0, or psi naught double dash x minus alpha square psi naught of x is equal to 0. That equation number 2, where that psi alpha, where alpha square be 2m divided by h cross square, that is v minus e, v minus e. Here we take negative as v minus e, okay, not confused. Then the solution of that of equation 2 would be on that of form, the solution that is psi naught is nearly equal to e to the power minus alpha x. The solution of that of equation be psi naught, that is nearly equal to e to the power minus alpha x, but we know, but when v, that is the potential, tends to infinity, similarly alpha tends to infinity, therefore psi naught tend to 0. That means the value of psi naught that represent the wave function of the particle outside that of box will be 0. Therefore we write psi naught of x is equal to 0 for what? For x greater than a, means the particle outside of that of box. That is the wave function represent the particle outside of the box. That is equation number 3. Now we take the wave function when that of particle inside that of box. We take wave function of the particle inside the box. Inside the box in the sense that x in that of region minus a less than x less than plus a, that region the particle exists inside that of box. So here we take general psi for that of particle inside that of box. For this region, that region, look at the figure, that is the region minus A to plus A. Inside that of region, the potential will be 0 as given. So for this region, potential is equal to 0. Hence, equation 1 of the form, equation 1 will be changed psi double dash of x plus 2m by h cross square e psi of x is equal to 0, that is equation number 4, or psi double dash of x plus k square psi x is equal to 0, that is equation number 5, where k square, that is 2m h cross square e. Now the solution of that of equation number 5, general solution of that of equation number 5 will be psi of x is equal to a sin kx plus b cos kx, that is the general solution of that of equation number 5. Now our task is to find out the arbitrary constant a and b, where a and b are two arbitrary constant whose values can be evaluated by applying the boundary conditions. That is the boundary conditions psi plus minus a is equal to 0, means at that case psi will be 0, at that point also psi will be 0, psi at plus minus a will be 0. This is the boundary condition. When we put that boundary condition in that of respective equation, what we have? Therefore we write, when we implement minus x for that of x, it will be psi at minus a, we get minus a sin ka plus b cos ka, or that value will be 0. Therefore minus a sin ka plus b cos ka is equal to 0, that is equation number 9. Again, when we put plus a, psi plus a, that is a sin ka plus be cos ka. Here when we put, that is minus a, cos of minus a, that is cos a plus, therefore that is positive. Again that value will be 0, therefore a sin ka plus b cos ka is equal to 0, that is equation number 10. Now this is equation number 9, that is equation number 10. From these two equations, when we solve means adding and subtracting these two, we get the value of these constants. Now adding and subtracting equation 9 and 10, we get a sin Ka, the value of a sin Ka is equal to 0 and b cos Ka is equal to 0. That is equation number 11, that is equation number 12. Now equation 11 implies that, from that of equation 11 implies that either a is equal to 0 or sin K is equal to 0, either a is equal to 0 or sin K is equal to 0. Again from equation 12 implies that either b is equal to 0 or cos K a is equal to 0. Now taking these two conditions, either a is equal to 0 or sin K is equal to 0, either b is equal to 0 or cos K is equal to 0, we obtain two class of solutions. So first class, taking these two equations we get two class of solutions. Therefore first class solution, first class we achieve either a is equal to 0, a is equal to 0, a is equal to 0, that indicates when a is equal to 0 sin K not is equal to 0, sin Ka not is equal to 0, and b not equal to 0 and b not equal to 0, which implies cos K is equal to 0, cos K is equal to 0. Okay, this is one class, let equation number 13. Next another class will be find out, let second class. The two class of solutions we derive when b is equal to 0, b is equal to 0, that indicates cos K not is equal to 0, cos Ka not is equal to 0. When b is equal to 0, that indicates a not equal to 0 and a not is equal to 0, which implies sin K is equal to 0, sin K is equal to 0. That is equation number 14. Okay, that is equation number 14. Now we should find out the solutions for first class and the solutions for second class. Now the solution for first class. Solution for first class. That is when a is equal to 0, sin K not equal to 0, b not equal to 0 and cos K is equal to 0. Now substituting the value of a is equal to 0 in that of equation number what? Equation number, its general solution, means that equation number 7, we put the value here to get the solution. Now substituting a is equal to 0 in equation number 7, we get, that is psi x, the wave function, b cos kx. Since b not equal to 0, that means cos Ka is equal to 0, which implies the solution of that of cosine function Ka, the general solution, that means the general solution Ka is equal to n pi by 2, where n stands for 1, 3, 5 ... which implies K is equal to n pi by 2a, n pi by 2a, the value of K. This is useful to substitute that value. Therefore The general solution of that of wave function psi nx will be b cos, for that of k we substitute n pi by 2a, that is n pi x by 2a, where n is equal to 1 3 5 dot dot dot. That is equation number what? Equation number 16. One class of solution we derive here, b cos n pi x. Next, second class of solution will be achieved. This is the solution where b is the constant. Our task is to find out the constant b also. Let me assume, since k is equal to n pi by 2a, although k square from that of equation, first equation, look here, we take the value of k square is equal to 2m by h cross square. Therefore, we use that relation, k square is equal to 2me by h cross square. In general, en energy for that of nth state, that is k square h cross square divided by 2m, or En is equal to n square pi square h cross square divided by 8 m a square. Just put that of value of k here, n pi by 2a, and its square, that is En, as equation number 17. Our aim is to get what should be the value of that constant and the energy term. Here is the energy term. Here is the energy term. Now we see that psi n minus x is equal to plus psi n of x. Since we implement cos of minus x is cos x, therefore psi n x is equal to b cos n pi x by 2a, has even parity and is represented by as psi n plus x is equal to b cos n pi x by 2a, equation number 18. We get that of constant b. So this constant b can be evaluated by using that of normalized condition. The constant b in psi n plus x can be evaluated by using the normalized condition. That is, we studied the orthogonalization of that of parity operators. So the normalized condition, integration of psi n plus star x psi n plus x dx is equal to 1 psi n plus star, this is the plus and its conjugate. Therefore the value of psi n plus conjugate, that is b, and here also b, that is the magnitude of b square, and integration from minus a to plus a cos square n pi x by 2a dx is equal to 1, or magnitude of b square minus a to plus a 1 plus cos n pi x by a divided by 2 dx is equal to 1. Cos square theta means 1 plus cos 2 theta divided by 2. Use that relation here, that is magnitude of b square here 1 by 2 to that of outside, then x plus a by n pi sin n pi by a from minus a to plus a is equal to 1, or magnitude of b square half, that value will be 2a plus that value will be 0 when we implement minus of minus a, that is a plus a, that is 2a is equal to 1. 2 to cancel out, magnitude of b 1 by under root of a, therefore the constant b is evaluated as 1 by root a. Therefore the wave function and its energy state psi n plus x given as 1 by the constant root a cos n pi x by 2a, and the energy state E n plus as n square pi square h cross square n square pi square h cross square divided by 8m a square, 8m a square. That is equation number 19. That is equation number 20. That is the solution for that of first class. We are taking the first class solution. This is the wave function, that one is the energy. This is the first class solution. This is the first class solution. Next we have to derive the second class solution. This is the first class solution. This is the wave function and energy. Next second class solution and its corresponding wave function and energy. Then solution for second class. Solution for second class. Solution for second class. Second class solution value as the second class solution value, that is b is equal to 0, cos k not equal to 0 and a not equal to 0, sin k is equal to 0. When you put b is equal to 0 for what equation? In that of equation number 7, that is the general solution of that of wave function. Inside that of region minus a to plus a, we put the value here. Okay, just use solution for second class, substituting b is equal to 0 in equation number 7, we get psi x is equal to a sin kx. Since a not equal to 0, sin k is equal to 0, sin k is equal to 0, which implies the general solution means sin k is equal to sin n pi by 2, where n stands for 2, 4, 6 ... which implies Ka is equal to n pi by 2, which implies K, that is n pi by 2a. We substitute the value of K n pi by 2a as required. Equation number 21. Therefore, the wave function sin of x, that is a sin For that of k we use n pi by 2a, n pi x by 2a. Here n stands for 2, 4, 6 ... That is equation number 22. And although we know k square 2me divided by h cross square, in general En, the energy term, that is k square h cross square divided by 2m, or En is equal to n square pi square h cross square divided by 8m a square. Just use the value of k here. This is the energy term, but our task is to get that arbitrary constant a. So for that of case, we see that here when you use minus of x, that is the odd parity, we see that psi n minus x gives rise to minus psi n of x. Therefore psi n x is equal to a sin n pi x by 2, n pi x by 2a, pi x by 2a has odd parity, and is represented as psi n minus x is equal to minus a sin n pi x by 2a. Now the constant a can be evaluated in psi n minus x by using the normalized conditions. So the constant a can be evaluated in psi n minus x by using the normalized condition. That is, normalized condition is what? Integration over psi n minus star, means its conjugate, psi n minus x dx is equal to 1. That is the normalized condition. Magnitude of a square, integration over limit from minus a to plus a sin square n pi x divided by 2a dx is equal to 1. Also sin square theta means 1 minus cos 2 theta divided by 2. That is magnitude of a square minus a to plus a, that is 1 minus cos 2a 2n pi x by a divided by 2 dx, dx is equal to 1. Previously we get also 1. Okay. Or a magnitude square divided by 2 integration from minus a to plus a 1 minus cos n pi x by a dx is equal to 1, or a magnitude square divided by 2, here that is x plus a by n pi sin 2n pi x by a limit from minus a to plus a 1. That value is what? That value is 2a is equal to 1. 2 cancel out, or value of a, that is 1 by under root of a. Now the constant a is evaluated as 1 by under root of a. Therefore the wave function and the energy term, the wave function and corresponding energy terms are written in the form psi n minus x is equal to 1 by root a sin n pi x by 2a, and the energy term En minus of x, that is 1 by that is n square pi square h cross square divided by 8 m a square. This is the wave function and energy term for that of second class solution. Now we get first class solution. This is the equation and this is the two class values. Here we get solution for first class and its wave function and energy term, and again for that of second class its wave function and energy term. Now we have to find out what should be the energy level diagram and eigen functions and probability distribution. We have to study it one by one. First, energy level diagram. Energy level diagram. How we diagrammatically show that energy level when that particle inside that of box. Okay. Look at these two equations in the sense that stands for equation let 23 and 24. That equation term, the energy term, that is n square pi square h cross square by 8 m a square, and here also the energy term n square pi square h cross square divided by 8 m a square. In these two equations, first class and second class, combining energy equations, from these two equations we get En, that is n square pi square h cross square divided by 8 m a square, where n stands for 1, 2, 3, 4 up to. As we taken the combining these two equations, two energy equations, this equation shows a particle confined in a box can't have any energy but certain permitted values. This equation that indicates the particular energy level is defined by the quantum number n. So from this equation what we conclude? This equation shows a particle confined in a box can't have any energy but certain permitted values. And the particular energy level, is defined by the quantum number n, by the quantum number n. N stands for particular energy level 1, 2, 3 like this. When for n is equal to 1, we prefer n is equal to 1. N is equal to 1 means E1 is equal to pi square h square divided by 8 m a square. When you implement n is equal to 1, corresponds to the ground state, and the states are 2, 3, 4 are the excited states. When n is equal to 1, n is equal to 1 means n is equal to 1, that stands for ground state, here, and 2, 3, 4 these are stands for excited state, Here n is equal to 1, the value pi square h square divided by 8 m a square, we assume it as epsilon naught be the ground state energy. This is the ground state energy, ground state energy, which is non-zero, that is non-zero. There will be some value that is not zero, that is a particular value will be achieved, and is called, this energy level is called the 0 point energy, that is called the 0 point energy, 0 point energy. Therefore, En can be written as, that is the ground state energy or 0 point energy, that is n square times of epsilon naught, n square times of epsilon naught. Let we prefer equation number 25. Okay, En is equal to n square epsilon naught. The allowed energy levels for the particle enclosed within the box is what? When n is equal to 1, it will be, when n is equal to 1, it will be epsilon naught. When n is equal to 2, it will be 4 epsilon naught. When n is equal to 3, that is 9 epsilon naught. Like this, these are the what? These are the allowed energy values for the particle enclosed within the box. For n is equal to 1, epsilon, 4 epsilon, 9 epsilon naught are the energy values. Now, the space between the two adjacent energy level, what is the space in between these two adjacent energy level? Let we prefer del En, that is n plus 1 state minus n state energy level. What should be the difference between these two? That is n plus 1 square epsilon naught minus n square epsilon naught. We get 2n plus 1 epsilon naught, where n stands for 1, 2, 3 ... And equation number 26. Here that equation implies that the energy level spacing is proportional to the series of odd numbers. 2n plus 1 means odd numbers, hence it is not equispaced. Therefore, the energy levels are look like this. The energy levels are diagrammatically show in this way. We show the energy level diagrams. This is n is equal to 1. This is n is equal to 1. Then n is equal to 2. That is for n is equal to 3. These are not equispaced, and these spaces are represented as like this. When n is equal to 1, what should be the energy values? These are the energy values as epsilon, the energy values like epsilon naught, 4 epsilon naught, 9 epsilon naught, like this. These are the energy levels. Now, what should be the Eigen function? What should be the Eigen function and probability distribution? Now, Eigen function. Eigen function. Eigen functions representing the particles like n is equal to 1, 2, 3 are in the form when psi 1 plus x, that is 1 by a square root cos pi x by 2a. When n is equal to 2, that is psi 2 minus x. For 2 stands for second class, means 1 by a square root sin pi x by a, and psi 3 minus x 1 by a square root cos 3 pi x by 2a. In this way the eigen functions are continued. So we graphically represent these eigen functions as minus a plus a origin. Here n is equal to 1, n is equal to 1, 1 by a cos a, this, and for n is equal to 2, n is equal to 2, we have this like this. For n is equal to 3, for n is equal to 3, we get n is equal to 3. This stands for minus infinity to plus infinity. These are the eigen functions. Now the probability distribution. Probability distribution means what should be the probability of finding that particle inside that of energy level diagrams. For the ground state, psi 1 plus x magnitude square is equal to 1 by a cos square pi x by 2a. Therefore at origin, at x is equal to 0, that is psi 1 plus x magnitude square is equal to 1 by a cos 0 is equal to 1, that is the maximum value, hence the particles probability is at the origin of the box. We get the probability of finding that particle in that of origin of the box. Hence the particle's probability is at the origin of the box. For n is equal to 2, that is first excited state, n is equal to 2, that is the first excited state. The probability density becomes becomes psi 2 minus x magnitude square, this is the probability density, 1 by a sin square pi x by a. Hence we conclude that the probability of finding the particle is different from different states, and this contradicts the classical idea that energy point inside the box is equally probable. But actually in that of case, that is not equally probable to finding that particle inside that of box. For that of different energy state, the values are different. When n is equal to 0 means at ground state it will be this, and when n is equal to 2 means the first excited state, it will be different. So it contradicts to the classical results. Now the probability distribution, graphically we plot it. The probability distribution zero minus a plus a, when n is equal to 1, the probability of finding that particle. When n is equal to 2, that is the probability of finding that particle. This stands for minus infinity to plus infinity. This is the probability distribution. How? We have to choose a particle inside that of box. What should be the probability of finding that particle? That is defined by using probability density concept, probability distribution, and this is the Eigen function. So, with the help of this visual lecture, we understand. Let's overlook one by one. Particle in one-dimensional box or infinite deep potential well. We take the potential region, time independent Schrodinger equation. What should be the wave function outside that of box? Its solution, and get the solution. And again, the wave function of the particle inside that of box means minus a to plus a region. This is the solution, and the arbitrary constant a and b are calculated by using the boundary conditions, and we get two class of solutions, first class and second class. We use these two class of solutions individually and get the solution of first class psi n and En, that is the wave function and energy is calculated, and normalized conditions used to get that of constant b, and finally the constant b is evaluated, and finally we get the wave function and energy state. Again, the wave function and energy state for that of second class solution will be achieved. Again, here the constant a is evaluated using that of normalized condition, and finally we get wave function and energy states. From these overall discussions, we get the energy level diagram combining the energy level terms of these two class of solutions, and we take the ground state energy, which is non-zero and also known as 0 point energy, and that energy state is given as n square epsilon naught. Epsilon naught is the ground state energy. This is the allowed energy values when n is equal to 1, n is equal to 2 and n is equal to 3, like this. This is the difference between these two energy levels. This is the odd one. Therefore, the energy levels are not equispaced. And Eigen function, its diagrammatical or graphical representation of that of Eigen functions using that equations, and the probability distribution, we check what is the maximum value and what should be the probability density for first excited state. From this we conclude that the probability density is different for different energy levels. That means it contradicts to the result of classical. So, this is the probability distribution. So, with this useful and informative notes, let me wind up this session. Thank you.